Welcome to the lesson 25 of industrial instrumentation. In this lesson, we will consider ultrasonic sensor, right. Ultrasonic sensors, ultrasonic measurements of flow velocity or ultrasonic based flow velocity we have discussed some time back, but in these particular lessons we will basically will discuss the basic principle of the sensors and how the transmitters, what is the principle of transmitters, its equivalent circuits, how the receiver works, and the various applications of the ultrasonic sensors like level measurements, crack detection, as well as the biomedical applications where the ultrasonic sensor plays a great role. So, that part we will discuss in this particular lesson. Let us look at the contents of this lesson. Contents looks like ultrasonic principle, what is the principle, how it works, that is actually we will discuss here. Then transmitter receiver we will discuss in details. Then equivalent circuit of the ultrasonic sensors we will discuss. Then its applications, both the level measurements, crack detection as well as biomedical applications we will all discuss in this particular lesson. Ultrasonic sensors, if I look at the ultrasonic measurement system consists of an ultrasonic transmitter, the transmission medium and ultrasonic receiver. Whenever there is an ultrasonic sensor, there must be a transmission medium, and ultrasonic we will see that later on. The ultrasonic is a very poor transmission in air. So, medium, there must be some medium, might be water, might be some steel, might be some alloy and so on and so forth. Especially the ultrasonic, signals, we will see that it is a great transmission, transmission extremely good in the case of, because ultimately we need some receiver where the signal will be received. Either the same signal can be used as a same transducer can be used as a receiver. So, in all the cases there should be good transmission, that means transmission power should not be lost substantially. So, that will not, it is not possible to detect either by the separate receiver or by the same receiver which is transmitting signal sometime back, like that. The commonly used ultrasonic sensors are the piezoelectric sensing element. These are most commonly used. You see here in the figure we are showing the piezo crystals. We are applying here. Let us look at. You see here, if I I am applying the signals. Let me take this one. Applying a voltage, signal here, I am getting a force here, right, and it is reversible. You can see that if I apply the force, I will get a voltage. That is the typical principles of the ultrasonic sensors or the piezoelectric crystals, I should say, right. It is a typical crystal. We are using that properties of the piezoelectric crystals to generate the ultrasonic signals, right. As we know, piezoelectric effect is reversible. The ultrasonic transmitter uses the inverse piezoelectric effect, as I just right now I told, that is if a voltage is applied to the transmitter, the crystal will undergo a corresponding deformation, right. If I apply a voltage to a crystal, so there will be deformation of the crystal. So, how can I utilize? Let us look at. You see, I have a crystal here, and take a different pen, crystal here. So, I have applied the voltage, right. If I applied the voltage, obviously what will happen, I will get a vibrations on this side, mechanical vibrations. So, these vibrations, now if I applied AC, obviously if I applied a high frequency AC here, I will get a vibration on this side. So, these vibrations will be transmitted on a medium. Now, if I put another receiver on the other side, so this will also vibrate with the same frequency, because there is a movement of the particle movement of the medium. So, obviously this will, this I should say the direct, indirect method, indirect way, that means I am applying a voltage, I am getting a force, and now the force is imposing on these crystals, which is a receiver, I am getting output voltage. This is basic principles of the ultrasonic transmitters and receiver. Though sometimes we will see that the same crystals are utilized for both transmission and for receiving the signals, right. The vibration of the crystal is transmitted through the media from one end to the other. Just we have shown that there is a vibrations and the signal, ultrasonic signals will move through that medium. Basic ideas and all this I am not discussing, because already we have discussed also, we have discussed the basic flow meters using ultrasonic sensors. Here actually I am going more on the sensor side, that means how actually what is the equivalent circuits, what type of signals it will generate, what are the basic application, I mean that type of things we will discuss in this particular lesson. The particle displacement sets up an accompanying pressure which is picked up by the receiver, right. Just I showed that it's a particle vibrations, okay, like it will vibrate like this one. So, this I have a receiver, this will also vibrate, because wave will, the ultrasonic wave will transmit through the medium. So, it is received by that receiver, and it will get the output signal. It might be it might happen in the separate ways. Suppose I am transmitting a signals which is a burst of signals, a short waves I am transmitting. So, it is getting reflected during transmission, it is working as a transmitter. So, when it is reflected I am coming back here. So, I can use as a receiver, right. The receiver use the direct piezoelectric effect, because if I use the term that if the with an electric voltage I am applying, I am getting the force, that is indirect. So, the receiver use the direct, so the receiver will use the direct method, right. So, one is indirect and is direct, so there is nothing, it is a reversible process that I want to mean. Direct piezoelectric effect and converts the force into the corresponding voltage. For transmitter I use some notation, X equal to D multiplied by V, and for receiver Q equal to D multiplied by F. The performance characteristics D for both the cases are same, right. Moreover, F we can write K multiplied by X, K into X into D into V, where K is the stiffness constant of the crystal. This is the equivalent circuit of a transmitter. I think we have a signal generators, okay. So, on the other sides you see we have M, B, 1 by K. What are these legends that will be shown in the next slide? This is equivalent circuit of a piezoelectric transmitter, right, which is actually ultrasonic transmitter I should say. So, it is in contrast, in context with the piezoelectric crystals I am discussing all this, where you see the Zg, the output impedance of the signal. So, let me go back again. Okay, Zg is here on the generator side, output impedance of the signal growth, mass of the crystals M, damping coefficient B, K the spring constant, Zm In is the input impedance of the medium, X dot is the velocity, and ideally we can assume always that Zg equal to 0 and Zm In, that means output impedance of the signal growth is 0 and input impedance of the medium is also 0. So, ideal equivalent circuit of the transmitter looks like this, right. So, taking account the other what we have assumed. Now, this is the equivalent circuit, this is equivalent circuit of the transmitter with M, B and 1 by K reflected in the primary side. If I reflect in the primary side, obviously I will get L1, R1, C1, okay, where obviously when I reflect the primary side, what is the relation between the what we had previously in the secondary side and what it has now in the primary side, that must be related by the some coefficients which is dk. L1 equal to M upon dk square, R1 equal to B upon dk square and C1 equal to D square into K, right. Now, overall impedance I should say 1 by Hs or 1 by Hs Sc plus 1 upon R1 SL1 plus 1 by Sc1. Therefore, I can say that H j omega, if I write in the j omega domain, so omega R1 C1 minus j all inside 1 minus omega square L1 C1 upon omega C plus C1 minus omega square L1 C C1 plus j omega square C C1 R1. Thus, we have two natural frequencies, series natural frequency which is 1 upon root over L1 C1 and the parallel resonant frequency omega p root over C plus C1 upon L1 C C1, all under the square root obviously. Now, you see the magnitude plot of this transmitter is like this one, right. It has significant, I mean there is some significance of this plot which will be discussed later on. And where at omega equal to omega n natural frequency magnitude is minimum, whereas it is maximum at omega equal to omega p. Assuming R1 equal to 0, you see this is a phase plot of the transmitters. So, we can see within omega and omega p it is a 90 degree plus 90 degree phase shift, and outside that range it has a minus pi by 2 phase shift. What does it mean? At omega equal to omega n, omega equal to omega p, the system is resistive, this is most important, and when R1 not equal to 0, the above diagram shifts towards the right hand side. So, this you see that it is working as resistive sensors. Okay. At omega equal to omega p, the system is resistive, and when R1 equal to 0, the above diagram shifts towards the right hand side. The circuit behaves as an inductor between omega n and omega p. Clear? In some part it is resistive, in some part it is inductive. Transmissions of ultrasound. How do you transmit this ultrasound signal? If P is the pressure or stress and x dot equal to u is the velocity, because x is a displacement, so we are taking derivative of that. So, the characteristics impedance Z equal to P by u, the power intensity W equal to P into u, average power intensity is given by W equal to 1 by lambda integral omega z dz lambda over the integration of the limit lambda to 0. It looks like this. You see the transmissions of ultrasound signal between two medium. Okay. You see the medium 1 and this is medium 2. These are crystals. Okay. These are reflected wave. We will see the lesions. What are the lesions? Where Z1 is the characteristics impedance of the medium 1. What is Z1? Okay, this is Z1. Z2 is the characteristic impedance of medium 2, right? And Wi is the incident power intensity and Wr the reflected power intensity, and Wt is the transmitted power intensity. Wi is the lesser than the power intensity generated by the crystal due to losses in the medium 1, right. Obviously, there will be some loss in the medium 1, and alpha r is the deflection coefficient which is given by Wr by Wi equal to Z2 minus Z1 whole square upon Z2 plus Z1 square. Alpha t is the transmission coefficient Wt by Wi 4 Z1 into Z2 upon Z2 plus Z1 whole square. And obviously, alpha r plus alpha t reflected and transmission, I mean if you take this coefficient, obviously these two will be 1 if there is no absorptions, right. If Z2 minus Z1 is large, then the mode of the incident power is intensity is reflected back, right. So, the characteristics impedance of the this you see this very important, while you will find we will see that while you are using this ultrasonic sensor for the level measurements, right. If Z2 minus Z1 is large, then more of the incident power it will be reflected back from the mediums 2, right. Using this principle we will make the level sensors, right. So, this is a typical property, even though sometimes it feels like that it is a bad quality, but this property will be utilized to make a very good sensors of the level measurements as well as crack detections in a metal. Clear? Now, characteristics impedance of the few materials. We will now jot down some of the characteristics impedance of the few materials. Quartz 1.5 into 10 to the power 7, then barium titanate 2.5 10 to the power 7, then polymer PVDF. We are using all SI notations, please note 0.4 in 10 to the power 7, steel 4.7 in 10 to the power 7, aluminum 1.7 into 10 to the power 7, bone 0.8 into 10 to the power 7, water 0.5 into 10 to the power 7, air 430 only, right. So, this property of the air will be utilized to make the good level measurement of any liquid. Most of the liquids I will find, I mean liquid is good, but in the most of the cases air is a very poor, I mean offering, I mean transmit, I mean characteristics impedance. Alpha R and alpha T for different interfaces. There are two interfaces of the two material, medium 1 and medium 2, alpha R and alpha T for the different mediums will be. This will give you how you can interface two different medium while you are transmitting the signal from medium 1 to medium 2, right. So, that is the reason alpha R and alpha T is necessary. So, it is the two different, we will take the combinations of the two materials, right. See quartz steel, so it is 0.27, 0.73, quartz water 0.67, 0.33, that means if you want to transmit, right. So, this is reflected is more than the transmittance, and here you see the quartz, the reflection is less than the transmittance, and quartz air obviously will shine extremely poor, say 1 and 1.1 10 to the minus 7 NU 10 to the minus 4. Thus, we can say that the air is a poor choice for transmission of ultrasound waves, right, as the difference of the characteristics impedance of air with others is very large, right. PVDF is a polymer, actually is used for biomedical applications. So, measurement of ultrasound, pulse echo technique is a piezoelectric crystals acting as a transmitter receiver is attached to the medium 1, will show the diagram. The characteristics impedance of medium 1 and 2 must be substantially different, otherwise cannot be reflected. First, the crystal act as a transmitter and it sent out a pulse, is a burst of signal, I mean burst of pulse, I mean it is very short duration pulse and it will remain silent for some time until unless I received all the signals, all the reflected signals, right. You will find that you will get repeated reflected signals. We will take the first one, which is, I mean received signals which has the highest intensity, other subsequent signals, reflected signals will have lower intensity, right, generated by the pulse generator with TW. You see these here, we are measuring scheme of ultrasounds, we are showing one time base here, it is same as the oscilloscope, as you know we have a time base there also. So, what to do from here also we have, I have two medium, medium 1, medium 2, we are just discussed these, I mean alpha R and alpha T for the two different mediums, the two medium. You see one reflected from this side, another one reflected for the medium 2, obviously this will take more than time and of lesser intensity. So, here you will find the intensity is much more. And with the first signal, you see that a signal will come, so it will first go, so signal will go and reflected back. After, I mean this signal again will come and reflected back. Obviously, the shortest time will be this signal, right, because ultrasounds will transmit and will silent for some time, right, until unless we will make all the measurements and next time again we will transmit a signal. Most of the pulse energy, what is this, I mean the surprise, what is echo amplifier? Echo amplifier is nothing, it is a amplifier, it is I mean operated only for the time when the first reflected signal will come, because the signal you may need the amplifications, that is the reason I need an amplifier here. So, that is the echo signal, that means the reflected back signal will be amplified and put here, and so we have pulse generators which will give you in the time base. It is in the vertical signals, the signals, what is the signal which is coming at the vertical plate? That is a signal that is reflected ultrasonic waves are coming at the vertical path, whereas the time base we are giving in the horizontal path. Principle is same as we have seen in the oscilloscope, right. Most of the pulse energy is reflected at the boundary of medium 1 and 2, clear? What is that? Most of the pulse energy will be reflected here, okay. So, signal will come, it will reflect it back and it will come down here, right. The crystal now acts as a receiver and receive a pulse, right. Initially it transmitted and remained silent, it will not transmit a signals until unless the signal is coming back from the receiver, from the reflected surface. That means, the junctions of the two surfaces, two different medium will work as a reflector of the ultrasonic waves. The time taken by the reflected pulse is T t equal to 2 I upon c, right. What is y 2? Because it will go and it will reflect it back. What is 2 L? If you say it is L small letter or 2 I, whatever it. So, it is the length of the medium 1, right, where I is the distance of the interface of the two medium from the crystals, right. What is that? Let us look at. I have deflected like this one. So, I have a two medium is here, right. So, I am transmitting a signal. So, its signal is coming reflected back. This is our L I, right, and c is the velocity of sound in medium 1, clear. Now, you see the reflected means of ultrasonic signals. This is very nicely we have shown. You see the first outgoing pulse will look like this one, obviously, because a part of the signal will be transmitted through the medium, to the junction of the medium, will go to the medium 2. So, this is the first reflected wave, it will come, then second reflected wave, then third reflected, all of different magnitude. So, we will first we will take this one and will not send any signals until unless all the signals are died out, all the reflected signals are die out. We can calculate that part, and accordingly my burst of signals which will go to the transmitter, because there must be some electronic circuitry which will transmit the signal, which will go to the, because ultimately I have to impose some vibrations. I can use some oscillators also there, right, electronic oscillators which will start to make the vibrations of the ultrasonic crystals, right. So, I can obviously I can program in such a way that the time taken, time in between transmission of two signals will be such that all the reflected waves will be die out by within that time. The repetition rate Tr should be such that all the reflected pulses of the interest have been observed before sending the second pulse, right. The transmit time Tt should be large compared to the pulse width Tw to avoid interference between the outgoing pulse and the incoming or reflected wave, right. So, we have a width. So, we have decided, I mean we are making transmitting time Td should be large compared to the pulse width to avoid the interference. So, we are making this large width. So, obviously, within that times we will transmit, right. What does it mean? It means, you see, I have a, it looks like this, that means I have a width like this one, right, because this I can program. So, during that time, this time all my signal reflected waves, okay, will be finished until unless. So, there is sufficient amount of elapsed time, my next pulse will be transmitted again. So, this is the transmission width, right. So, it is a pulse width Tw to avoid interference between the outgoing pulse and the incoming or reflected pulse. This is all about, right. Now, applications of this type of ultrasonic signals, let us look at. The method discussed can be used to make the level measurements, okay, especially the level measurements of a liquid. I mean, if I need a with precision and fast measurements, because you know the liquid there are various types of measurement of the level measurements. We have a steel tape and the rulers, that type of things are there. Scale and steel tape, which is used mostly in our country, you will find anywhere in the municipality tank. So, huge tanks, so that can be utilized for measurements. That means, it is other way. You will see the scale will be when it is empty, when the tank is empty, all the indicators will go up, okay, and when the tank is full, the indicator will come down. It is a mechanical indicator which is connected by a counterweight. So, that it will, whenever this level is up, level is filled up, so it will switch off. Now, there are many other, there are capacitive method of level measurements we have seen, there are method of so many other methods of level measurements. we have pneumatic level measurements. That means I mean it looks like this. You see, I have a vessels. Okay. So, I will put a pressure on this one. So, there is a float. So, this will, so if it goes up, so it will put a pressure on the bellows, right. So, this can be transmitted, okay, to indicate on a Bourdeau gauge or a to show the pressure, because so this pressure gauge will be calibrated in terms of levels. You cannot use both the cases. That means, you cannot use both the Bourdeau gauges and the and the C type Bourdeau tube. You have to use either you use bellows, because bellow will try to expand. So, that if you connect an indicator, it will show you the level, or if you connect it to the some Bourdeau gauge. So, there is a deflections of the free end of the C tube. So, you will get the measurements, and that pressure can be calibrated in terms of level. So, there is a lot of the, but you see the most of the cases, this is most important, that the ultrasonic measurement you will find is very non-invasive type of technique, right. You do not have to, your sensor should not be in contact with the, not necessarily should be in contact with the liquids or any other materials. You see, this is a typical example of a level measurements. It looks like this. You see, this is a liquid, this is our vessel, in which I am interested to make the measurement, right. So, there is ultrasonic signal. So, I am transmitting these signals and reflected back. As I told you, the pulse width will be sufficiently large. So, that all the reflected waves will be collected here, okay, before I send the next pulse, right. So, this time will be measured, okay. So, time will be what? So, as the level goes high, okay. So, as the level goes high, the ultrasonic waves will take more and more time to travel the distance, right, and will be reflected. So, I will calculate the T, as I told you, T equal to 2 I by C. So, if this is I, right. So, by C is the velocity of ultrasonic waves in this particular liquid, right. So, I will get direct measurements, because how? If I measure T, so obviously I will be what? I will be level. So, I will be T multiplied by C divided by 2, is not it? But there is a precision of measurement, because you see this signal will go so fast, the entire accuracy will lie on how accurately you can measure the T. That is most important, right. Even though it looks very simple, when you show like this one, but actual implementation is quite tough in that sense. Clear? Now, you see why I have installed the crystal at this side. I could have installed on this side also. I could have installed the crystal on this side, is not it? The ultrasonic wave also will come here and reflected back, but this is the liquid, this is my liquid, right. So, let me take the new page, so that will be better. You see, this is my liquid, and this is air. This is the top surface of the vessel, top surface, and this is the top surface of the liquid. If I install a ultrasonic sensor here, then what will happen? Either way it is same, because as the liquid goes up and up, what will happen, that again that this it will reflected back from this side. Because you see, due to the difference of the characteristics impedance, the ultrasonic will be reflected. Here also the sound will be reflected, but as I told you that it is very difficult to launch these ultrasonic waves in air. So, that is the reasons we have put the crystal down, so that it can be easy to transmit the signal through the liquid rather than transmitting through the here. Clear? It is to be noted that the crystal must be placed at the bottom, not at the top, just we have what we have discussed right now, right. If placed at the top due to presence of air, no wave will be able to propagate, thus giving us erroneous measurements, right. That is the reason we have installed at the bottom of our vessel. Now, ultrasonic waves, as I told you earlier at the beginning of the lessons, it is also used for the crack detection. You see here what will happen, ultrasonic waves will come. If there is no crack, so what will happen? The signal will transmitted like this one, if there is no crack. If there is a crack, then what will happen? So, again there is a difference of the characteristics impedance here. So, what will happen? So, it will come, will reflect it back through this one. If I know that, sorry, if I know the time, sorry, if I take a, so what will happen? It will go, it cannot move through air, so it will reflect it back. So, if I measure the time, I can exactly locate where the crack is, even though if it is from outside, it might be invisible if it is the crack is inside, right. This is a very excellent technique. I mean, we have different techniques of crack detection. So, we have the detections of the, we have method of X-ray and all this thing, but it is very cumbersome. You know, you have to, I mean, take an X-ray, it is hazardous, you have to shield the people who are working there, then I mean, you need a plate where to develop all those things, but that is not necessary here in the case of ultrasonic signals if you use it for crack detections. Here crack or gap acts as a second medium and thus help us to detect where the crack has taken place. Ultrasonic can also be used in the measurement of flow. We have seen that we have transit time ultrasonic flow meter, Doppler shift ultrasonic flow meter, those we have already discussed. Though we have not discussed in details of the transmitter and receivers, that we are discussing in the ultrasonic sensor itself. That actually is a part of flow measurements, that there is a little scope of discussing of all this sensor as such, as it's as a whole as a transducers, flow transducers we have discussed the ultrasonic measurement of flow. Advantages, what are the different advantages? It is easy to direct and focus a beam of ultrasound as diffraction of these waves are small, okay, due to their short wavelength, diffractions is small, okay. Ultrasonic waves can easily pass through the metals, that is a great advantage. This helps in mounting the measurement system outside the system, and it will not lead to the development, it will lead to the development of the non-invasive techniques of measurement or non-invasive sensors. This is a terminology we are calling in non-invasive measurement, okay. So, this is non-invasive measurement techniques we are utilizing for ultrasonic waves, I mean making the ultrasonic measurement, because I can install it outside, I do not have to install anything inside. You have seen in all the pressure, all the level measurements except capacitors obviously, but capacitor is not a problem. I mean shielding, parasitic capacitor, all this comes, I mean great problem in the measurements. We need very accurate LCR meters or accurate bridge and all this is not necessary in the case of ultrasonic measurement. Special applications, ultrasonic applications, there are special applications of the ultrasonic waves. Ultrasonic sensors have wide applications in biomedical instrumentation, right. Measurements of blood flow, there are, I will discuss 3 different major applications of ultrasonic waves in biomedical instrumentation. Measurements of blood flow in the artery, determination of the blood pressure, and ultrasonography. Though ultrasonography I have not discussed the typical ultrasonography, I mean abdomens, ultrasonography, all those things. We will discuss some part of the ultrasonography, because it is a huge subject. You can take reference to any books, I mean textbooks. Determination of blood pressures, how the blood pressures will be. You see, these are typical, I mean typical diagrams of ultrasonic determination of blood pressures, right. So, here you will find that I have an ultrasound sensor, okay, and we have a ultrasound, this is a blood flow, and we have a ultrasound 8 megahertz detector also. These 8 megahertz signals, and we have a 8 megahertz detector also, amplifier and detectors. This audio amplifier, audio outputs, it is going to a headphone. This is actually, please note, this is a headphone, right. This is a headphone. We can, I mean, by listening to the sound, I can tell what is the pressures. Okay. This is how blood, and the blood is flowing to this artery. You see what will happen, that 8 megahertz incident ultrasound will come and in the blood. So, they will be reflected. Now, what will happen, you see here I have a skin here, because we have to put outside the skin. So, it is a non-invasive technique very much. So, we will look at the sound, we will listen to the sound. During the opening and the closing of the valves, I will get a signals of the, during opening I will get a larger amplitude signals, and during closing I will get a short amplitude signals. So, by this I can detect the ultrasounds and measure the pressures. Okay. So, these frequencies, this delta f is now converted into the audio output. So, delta f will be different, right. The measurement scheme employs a transcutaneous Doppler sensor which detects the motion of the blood vessels walls at various states of occlusion, right. Two small ultrasonic crystals 8 megahertz used as a transmitter as well as receiver. The transmitted signal from the Doppler ultrasonic is focused on the vessel wall and the blood. The reflected signal is detected and decoded, right. Decoding means, that means I am decoding in, converting into the amplitudes and all this frequency dependent, frequency voltage converter, that type of signal. Difference between the transmitter and the received signal is in the frequency range of 40 to 500 hertz and is proportional to the velocity of the wall motion and the blood velocity, right. When cuff pressure is above the diastolic, but below systolic, the vessel opens and closes each heartbeat as the pressure in the artery also oscillates below and above the external cuff pressure. This opening and the closing are determined by the ultrasonic systems that I show. Yeah, that means the two different waves, and during openings I will get a signal like this one. Sorry. So, I will get a signal which looks like during opening, and during closing I will get again during opening, so opening and close, right. So, this type of signal I will get. As pressure is increased further, the time between the opening and closing decreases and the reading indicates the systolic pressure, right. Conversely, when we decrease the pressure in the cuff, the diastolic pressure is recorded, clear. Now, advantage, what is the advantage of this system? There are some disadvantages also. Let us first look at the advantage. It can be used with the infants and hypotensive individual, that with pressures, persons with a high blood pressures. As you know, the medical, for a healthy person the blood pressure should be within 80 to 120, right. So, but some people have very high blood pressure, so for that type of patients we can use. Also, it can be used for infants. Can be used in the high noise environment, because you see all this this other type of measurement techniques what they are used, actually it depends that the physician must locate the time when the valves are opening. They must locate the barometric pressures, the manometric pressures when the valves are opening, right. So, it is sometimes very difficult if it is a noisy environment. So, it is quite immune to noise, outside noise, environmental noise, okay, which is very common in hospitals and all these things. So, it can be nicely utilized in that type of environment, or that type of places. But what is the disadvantages? Disadvantages: the movements of the subject's body cause the changes in the ultrasonic paths between the sensor and the blood vessels. Obviously, everything will change. So, the patient should some steady conditions, you should not lie. So, it is very difficult, obviously, though we are saying that it is very contradictory. We are saying the infant we can use, but in some cases we can utilize this type of measurement. Now, blood flow meters, you know, these flow meters is basic principle is same, transit time flow meters and the flow meters like Doppler shift flow meters, but the same principles also used for measurements of blood flow or the measurements of blood in the artery. Blood flow measurements using the ultrasonics can be done by the following: transit time measurement flow meter, Doppler ultrasonic flow meters, Doppler shift. This we have discussed very details in our flow meter lessons. So, I will not go to much details of this one. In context with the biomedical instrumentation, I will discuss something, nothing more than that. You see, these are ultrasonic transducers configurations. We are using different configurations of the ultrasonic users. Transducers ABCD. What this? Let us look at. Case A, the transit time probe requires two transducers facing each other and the path length between them is L and are inclined to the vessel axis at an angle theta. We know, if you recall, go back to the ultrasonic, you see the transit time principle is something like this. Okay, I have a vessel like this one. Okay, so I have a signal always will be inclined. Okay, I have a sensor here. So, it is this make an angle of theta, right. That is actually I am telling. That means, what I am telling here, for case A, the transit time probe requires two transducers facing each other. Obviously, you see that you remember in the I have two sensors, liquid is flowing through this. I have one sensor here and another sensor here, right, facing each other, clear. The transit time probe requires two transducers facing each other and the path length between them is L and are inclined to the vessel axis at an angle theta. The shaded region is representing an acoustic pulse, right. What is that? Let us go back. Shaded region is acoustic pulse. For transcutaneous probe, as in B, both the transducers are placed on the same side. They can be placed on the skin and the beam intersection region is shaded. Let us go back. Okay, this is a beam intersection region. So, two ones are placed. Okay. So, for transcutaneous probe, as in the B, both the transducers are placed on the same side and they can be placed on the skin. So, that we are utilizing the reflection from the blood, from the end of the artery like that. Intersection region is shaded, right. For case C, we can use a lens which helps to focus and narrow the beam. Sometimes we need to narrow the beam, since it can be utilized to do that. Case D is used for pulse operations. In this case, the transducer is loaded by the backing it with a mixture of tungsten powder in epoxy and a shaded region is shown for a single time of range grating. Okay. Now, the Doppler ultrasonic flow meters we see here, we have an oscillators. I always encourage that those who are listening to this particular lesson, they should go back to my the lesson on the flow measurements using ultrasonic principles. Okay. So, all the things will be discussed in great detail there, right. So, is the Doppler ultrasonic blood flow measurements, the principle is same. Okay. There are two types of frequency we will get zero crossing detectors. We have an low pass filters and output detectors, because the added frequency will be deleted when the difference of frequencies will be delayed, which is very small. So, that will be passed, all other frequencies will be stopped. So, this is actually the entire scheme of our ultrasonic flow meters using ultrasonic measurements of blood flow using the Doppler shift method, right. You can see here. So, we have a detector. So, then after that frequency will be lower. So, we have audio frequency amplifier. Detector can be simply a diode detector. So, obviously, what will happen that the output signals what will get a low frequency, and obviously, I can use an audio frequency amplifier there. You see, this is the audio frequency amplifier. We can have audio frequency output or speaker output also. Okay. and we have a zero crossing detector, then low pass filter, then we can get the output recorder, because this will I will get a signal. This I am getting audio signals, this I am getting electrical signal again here, which can be recorded, right. For Doppler flow meter, we know that F d by F o equal to u by c, where F d is the Doppler frequency shift and F o is the source frequency, which is basically ultrasonic frequency. U is the target velocity and is the velocity of sound. Okay, sorry, so it is source frequency, not velocity. Is F naught is the source frequency or the frequency of the ultrasonic sensors. For blood flow meters, the blood cells act as the particulate matters which form the reflecting targets, right. Because as you know, in the case of Doppler shift flow meters, I mean in the case of transit time flow meters, is basically used in the case of clean liquid, whereas the Doppler shift flow meter will not work. With that we have discussed in details, that it will not work until unless there is some suspended particle there in the liquid itself. If the liquid is flowing through the pipe, there should be some suspended particle, whatever small it may be, but that particle will be missing here in the case of the blood flow measurement, but the blood cells will act as a particulate matters which form the reflecting targets, right. From that actually the ultrasonic waves will be reflected back. It's excellent, okay, is not it? Okay, there is sometimes with that time we have discussed that the two different flow meters, because we do not know what type of liquids flow we are measuring. Sometimes the liquids might be very clean, suppose in the case of water, okay, or some other liquid, but sometimes it may have slurries, it might have some suspended particles, but if the liquid is extremely clean, I cannot use the Doppler shift flow meters. But that I mean principles is purposefully we are utilizing here in the case of blood flow measurement, right, where the cells will act as a reflector of the signals, ultrasonic signals which is transmitted from the transmitter. In the arrangement shown in the figure, frequency shift occurs twice, once between the transmitting source and the moving cell, correct. Second, another between the moving cell and the receiver, right. One is the moving between the transmitter source and the moving cell. Moving cell means moving blood cell, right. Its moving cell means moving blood cell, because obviously when there is continuous flow of blood through our artery, right. So, there is the cells are also which is continuously moving through the artery. So, another between the moving cells and the receiver. So, of F d by F naught equal to 2 u by c, as c is much greater than u, okay, velocity of the ultrasound must be much higher than the velocity of the blood flowing in the artery. So, what I can say that taking angle factor theta, the angle between the beam of sound and the axis of blood vessel, F d equal to twice F naught u cos theta by c, equation number 1, and as in the figure, the ultrasonic waves are transmitted to the cell which reflects the Doppler shifted wave to the receiver, right. As in the figure, the ultrasonic waves are transmitted to the cell which reflects the Doppler shifted wave to the receiver, right. So, that means I have ultrasonic waves, it is getting reflected and coming to the receiver. How does it look? Looks like this one, ultrasonic waves are there, okay. So, I have a source here, sorry. So, I have a source and I have a receiver here, ultrasonic waves I am transmitting, okay. So, it is getting here reflected back from the blood vessel, this is our blood vessels, blood cells rather I should say, blood cell, right, reflects the Doppler shifted wave to the receiver. So, this is getting deflected, I am getting here, it is getting reflected. The amplified radio frequency signal plus the carrier signal is detected by the produce and audio frequency signals, the basic principles of a audio, I mean our heterodyne receivers, okay. This classical methods actually utilized here also. AF signals given by equation 1. Now, ultrasonography, you see this is a I should say the last example of a this is a very wide subjects, its in-depth study is very difficult to accommodate in this particular fag end of the, I should say, of this particular lesson, but it is extensively used for measurements of many to know, especially when the child is in the womb of a woman. So, that time also it is utilized to know the health of that type of that baby in the womb, right. Anyway, there are other applications of the ultrasonography, we will discuss that part. Okay. So, you see the brain medicine, a mode scan of the brain midline. I have a receiver, transmitters. Okay. So, transmitting signals, it is transmitted. Then I have oscilloscopes, I have a sweep as usual. Okay. I am giving the vertical plates, this I am giving in the sweep, I am giving to the horizontal plate. I have to know, I have to make it stationary, because the signal is to be stationary. You know, that is the basic principles of the sawtooth waveform when we give to the horizontal waves, horizontal plates, right. So, that is actually utilized here. A mode scan of the brain midline. The appropriate electronic circuit can be used to pulse the ceramic in order to transmit a short pulse of ultrasonic energy. Okay. Always please remember, in all these methods we are always transmitting a short burst of the energy. Okay. How does it look? We have seen that, so already we have shown that we are transmitting signal looks like this. Then it is getting reflected with slower and lower and magnitude. Again I will transmit, this is the one width. Again I will transmit. So, this is a short burst of signals, is not it? It is not a continuous signals. You cannot make if you transmit a continuous signal, nowhere you can make the measurement. Clear? If first act as a miniature loudspeaker and then switch to act as a microphone to receive signals reflected from the interface of various tissue types, right. I can use a speakers also, and transmission, and for receiver you can use a microphone. Ultrasonic energy at the levels of medical imaging causes no harms to tissue. That is very important, because any other methods will give you harm the tissues. So, ultrasonic energy will not harm the tissues, because whenever you are using in medical instrumentation, you have to look at the safety, that it should not harm the human being, it not damage anything. So, those part you have to. This is an A mode device which shows eco-intensity as an XY plot. So, we have shown Y we are giving the amplitude of the reflected waves, and X plates we are giving the sweep. So, I will get a stationary waves. Okay. This is some information, I mean B mode ultrasounds imaging, intensity informations. Okay. Looks like this. This is known as B mode ultrasonic imaging techniques, which shows two-dimensional shape and reflectivity of the objects by using multiple scan paths. This type of simple device is seldom used now and has been replaced in more elegant systems. So, with this I come to the end of lesson 25, which is on the ultrasonic sensors. Welcome to the lesson 26 of industrial instrumentation. So, in this lesson basically we will cover nucleonic instrumentation. Let us look at nucleonic instrumentation. Means that we will use some radioactive sources, and there will be corresponding detectors, and there are some advantages of this this type of instrumentation, because we have seen that in the lesson 25 we have covered ultrasonic instrumentation. So, there are some typical advantage of the ultrasonic, but there are some cases like if you want to launch that ultrasonic waves in air, it is just impossible, where the radioactive rays can move through air. So, that is a great advantage of this particular instrumentation. So, it is to be covered very extensively. Let us look at the contents of this particular lesson. Contents: principles of nucleonic instrumentation, radioactive sources, radioactive source elements, what are the different elements which will code or which will make the radioactive sources, basically radioactive sources means alpha, beta, gamma rays, but what are the elements which will actually used for actually used in the nucleonic instrumentation that we must study. Its application in industrial instrumentations, that means you will find the label gauge, there is typical applications of the measurements of label, then typical applications of the measurements of the coating of sheets in the rolling mills. So there are various applications we will find in this particular type of instrumentations. So atomic weight might be same, with the densities, and density might be different, but the atomic weight can be the same. For level measurement, we use the following scheme. This is a scheme of the level measurement. So we have a source, you see here, we have a detector here, okay, and so this is a level measurement using nuclear instrumentation. So I have a liquid here. So how it works, let us look at. When passing through the fluid, the absorptions will be more, and hence the amplifier output forces the stepper motor to move the source and detector to move upward, right. You see what will happen. So when passing through the liquid, this will, so it will always try to move this stepper motor to move it upward, right. When they reach the interface, the absorption falls, and thus we know that the level is reached. Clear? Let me go it again. So the basic principle is something like this. These two systems, this let me take. That means this stepper, this source and detector will be initially at the bottom here. Okay. And please note that in the nucleonic instrumentation, so the hazard is a great problem. So you have to think of all this whenever you are using what type of radioactive materials you are using. Though the half-life and all this thing is not that large, but the amount of rays you have to think of. So the proper hazards, and it's sometimes there is environmentalists are there. So until unless you can manage with some other instrumentation which is non-hazardous, like ultrasonics and any conventional instrumentation of level gauge or density measurement, that is to be used. But in some situations, as I told you, like the detections of the leak in the pipe underground, or suppose in a closed containers, I want to know the level of the liquids and all these things. It's very difficult to know, especially it is sealed. The container might be closed, it does not matter, because if I have a inside electronics already installed inside, so I can sensor installed inside, I can detect. But if it is a separate container, suppose a cylindrical drum, I want to know how much the liquid contains, which you cannot see from outside. For that type of situations, I can use this type of radiation technique or technique. Okay. So this is to be basically, you have to be careful. That means that I told you several times. That means if I can manage with other instrumentation systems, conventional non-hazardous systems, we are not supposed to use radioactive sources, right. So with this I come to the end of this lesson 26.